Polar Gigantism. Imagine you're stranded in the Antarctic Ocean, and you make the mistake of looking down into the water beneath you. You'd expect tiny fish, maybe clouds of microscopic plankton. What you actually find is something far more unsettling. Spiders, with leg spans longer than a dog, are crawling across the seafloor. Jellyfish, with tentacles longer than blue whales, are drifting silently past. And even the most normal-looking fish are just wrong. Too big. All of it too big. And every single one of these things is real, because in the coldest oceans on Earth, evolution doesn't slow down, it goes completely off the rails. This is Polar Gigantism, a phenomenon most people have never heard of, operating in a world most people will never see. You'd think in a place where everything is freezing and food is scarce, animals would shrink to conserve energy. But the complete opposite happens. Cold water turns small things large and large things enormous, creating supersized versions of creatures that are already strange enough at normal scale. So why does this happen at all? The colossal squid. To understand Polar Gigantism, start with its most extreme example, the colossal squid. Most people assume the colossal squid is a product of the deep sea. It's not. Colossal squids live almost exclusively in the oceans surrounding Antarctica, swimming in waters at or near 0 degrees Celsius. Due to salinity, the water doesn't actually freeze at that temperature, but it's still an environment that would kill most animals outright. Here's the key. Colossal squids are actually a type of glass squid. Glass squids are a family of small, translucent creatures, delicate, see-through, and typically no larger than your hand. So how did one branch of this family become the largest invertebrate on Earth? Cold water holds vastly more dissolved oxygen than warm water does. And for almost every animal on the planet, larger bodies demand more oxygen to keep their cells alive. In warm tropical oceans, there simply isn't enough oxygen in the water to sustain something truly massive. But at 0 degrees Celsius, oxygen is effectively unlimited. And when you remove that limiter, size has no ceiling. Over millions of years, the Antarctic environment pushed glass squids toward larger and larger bodies. As they grew, transparency became useless, so their bodies traded it for thick, insulating flesh instead. Their skin turned deep red, absorbing bioluminescent light from prey rather than reflecting it. When you're big enough that almost nothing hunts you, you stop hiding from predators and start hiding from dinner. The colossal squid is also a rare case of double gigantism, combining polar gigantism with deep-sea gigantism, since it lives deeper than even the giant squid. This stacked effect is almost certainly why it outweighs the giant squid by nearly double, tipping the scales at over 500 kilograms. But if a squid the size of a car isn't enough to convince you, wait until you see what's crawling across the seafloor beneath it. Sea spiders, the size of dogs. Meet the sea spider. In a coral reef, sea spiders, technically pycnogonids, not true spiders, measure about 1 to 2 centimeters across, roughly the size of a house spider. Find the exact same family of animal in Antarctic waters, and it spans over 60 centimeters. The same creature, a completely different scale. The mechanism is identical. Cold water, more oxygen, and these animals breathe directly through their legs. Those impossibly long limbs aren't just for movement, they're the respiratory surface. More leg means more oxygen intake, which means the size ceiling rises even further. What do they do with all that size? They don't fight, they stalk. Antarctic sea spiders move across the seafloor on those stilt-like legs, stepping over sponges and corals, and then extend a long proboscis directly into the body of a starfish and drink. And the starfish they're drinking from? Those aren't normal either. Starfish with 50 arms. Antarctic starfish didn't just grow larger. Evolution kept adding arms. Some species carry more than 50, compared to the standard 5 of their warmer water relatives. They're aggressive predators, not just scavengers. They'll consume other starfish outright. In Antarctic terms, the most armed individual wins. These animals also live dramatically longer. A tropical starfish survives roughly 5 years. An Antarctic starfish can live over 40. Slower metabolism, more stable environment, more time. Polar gigantism doesn't just scale bodies, it scales lifespans. But of all the creatures Polar Gigantism has produced, makes the point more dramatically than an animal that most people wouldn't even consider dangerous. The longest animal on Earth. The full reach of Polar Gigantism becomes most visible in a single, staggering fact. The longest animal ever recorded is a jellyfish, the lion's mane jellyfish. A cold water species found in Arctic and subarctic waters, produces tentacles that exceed the length of a blue whale in total body span. It's the longest animal on the planet. Compare it to a closely related warm water species, the blue jellyfish, and the difference is striking. Same evolutionary lineage, completely different scale. The only meaningful variable is water temperature. Why cold makes giants. High oxygen availability is the foundation, but it's not the complete picture. In cold water, metabolism slows dramatically. Large bodies burn less energy per unit of mass. They become more efficient, not less. In warm water, a massive body is a liability. It demands constant fuel, overheats, and fights against a metabolic system running at full speed. In cold water, it's an asset, the same size that would drain an animal in the tropics, sustains one in the Antarctic. The environment also provides unusual stability. Antarctic ocean temperatures barely fluctuate. Pressure is constant. Seasonal variation is minimal. There's no evolutionary pressure to stay small and fast and adaptable, so animals didn't. They optimized for mass, longevity, and endurance instead. This is also why Polar Gigantism is exclusive to cold-blooded animals. Warm-blooded creatures face a different constraint. They generate their own body heat, and that requires constant caloric input. In food-scarce polar environments, every extra kilogram of body mass comes with a metabolic bill that can't always be paid. Warm-blooded polar animals do get larger, but through a separate mechanism called Bergmann's rule. Bigger bodies retain heat more efficiently, which is why polar bears dwarf temperate bears and emperor penguins tower over tropical species. But Bergmann's rule has a ceiling. Being warm-blooded means the energy cost of mass scales upward without limit. You can get big, but you can never go colossal. The ocean doesn't play by those rules, and the effect doesn't stop at animals you can actually see. Even plankton. Antarctic copepods, the polar version of plankton, rare, nearly 10 times heavier than their tropical counterparts. Most copepods are invisible to the naked eye, measuring under a millimeter. Antarctic copepods can reach a full centimeter, still tiny by any reasonable standard, but in the world of plankton, genuinely monstrous. But here's the twist: not everything in the Antarctic got bigger. A few species went the exact opposite direction. And the reason why is just as fascinating: the exception. Polar dwarfism. Not everything in the Antarctic got the gigantism treatment. A small number of species went the opposite direction. Certain Antarctic fish, including some icefish and snailfish, in environments where food disappears for months at a time. A smaller body reaches maturity faster, reproduces sooner, and survives lean periods more easily. When scarcity is the primary threat, compactness is a survival strategy. Polar dwarfism is rare, but it demonstrates that evolution in the Antarctic isn't simply running one program. It's solving specific problems, and size is just one of the tools. And when you look at how slowly everything moves down here, you start to realize these animals aren't just big, they're ancient, frozen in time. Cold doesn't just affect how large these animals grow, it affects how fast the species themselves evolve. When metabolism slows, so does everything else. Chemical reactions, reproduction, generation time. A single generation of some Antarctic animals spans decades. Evolution, already measured in millions of years, slows further still. The result is that many Antarctic species are living fossils, nearly identical to ancestors that swam under this ice tens of millions of years ago. Sea spiders, sea urchins, and certain fish lineages have barely changed since before humans existed. In a stable environment with no forcing function for change, there's no reason to change. These creatures are fine-tuned for a world that has remained consistent, cold and oxygen-rich for geological timescales. It has worked, without interruption, for millions of years, which sounds impressive until you realize that the very thing that made them perfect is now their greatest weakness. The vulnerability polar giants are built for one thing: stability. Their size, their metabolism, their entire biological architecture assumes water that stays cold, dense, and saturated with oxygen. Warm that water even slightly, and the system begins to fail. Oxygen levels drop. Metabolisms accelerate. Bodies that were assets become liabilities, too large to sustain, too specialized to adapt. This is already being measured. In regions where Antarctic water temperatures have risen incrementally, maximum sea spider body sizes are declining. What took millions of years to build is responding to change within decades. If warming continues, colossal squids face a future in which the very conditions that made them possible no longer exist. The oxygen that freed them from size constraints disappears. The cold that made their mass efficient becomes warmth that makes it fatal. These animals are not threats. Total recorded human fatalities from colossal squid attacks, 0. They live in one of the most remote environments on the planet and have no interest in us whatsoever. They are, instead, something rarer, living evidence of what evolution produces when the rules change.